This is a clean glean of arc length. Let's first do some reviewing. OpenStax, Calculus Volume 3, Section 3.1, introduced vector-valued functions. We can consider when the vector is a 2-vec or a 3-vec, that we write down an r-vec. We make it dependent on a parameter t, and set it equal to components f of t and g of t. When we sketch out the graph of this vector-valued function, we get a curve C. In this case, since there are just two component functions, this is a plane curve. When you fix the parameter t, you're locating a point on the curve. Therefore, the r-vec of t may be referred to as the position vector. And to identify a position on the plane curve, we need to specify components. These scalar-valued functions, f of t and g of t, therefore play the role of component functions. Good. Now, we have a plane curve or space curve. Here we're looking at a plane curve. May be given by a vector equation. Thinking back, Calculus 3 began with looking at parametric equations to parameterize a curve. Looking at the vector equation, letting x equal f, letting y equal g, exactly produces the parametric equations. So really nothing new is going on here. Let's continue with our review. After introducing parametric equations, the first thing that you do is, well, how do we do calculus? What's my dy dx? Same thing happens here after introducing a vector-valued function. We went into 3.2, calculus of vector-valued functions. How do we take a derivative? We saw that by a theorem, a derivative of a vector-valued function is supremely easy. You simply differentiate its component functions. Very nice. The third review item, again, going all the way back to the beginning, section 1.2. 1.2 went over the notion of arc length. That is exactly what this video is on. Again, note that we can describe a plane curve using parametric equations, as we did back in 1.2, or now in Chapter 3 using a vector equation. In either case, it comes out back from 1.2 that the arc length takes this form, where we are differentiating the parametric equations. Here on the plane curve written out as a vector equation, this integrand may be formed up by using a derivative on the position vector. And that is exactly what happens. Here we are now in 3.3, and we're seeing that the arc length of a curve where the parameter is taken from A to B is given by exactly the same integrand. Looking at this integrand, this is the radical of a sum of squares. The quantities being squared are derivatives of the component functions. In other notation, that is exactly the same thing as the norm of a derivative on the position function. Nice. So this is exactly what we saw in 1.2. There is one caveat, that we want the curve to be a good curve. A fancier name for good is smooth. And a curve is a smooth curve if, 1, the position vector is differentiable, and 2, its derivative is never the 0 vector. This has the nice property that when we go and try and compute arc length, that our integrand is never a value of 0. If the integrand was a value of 0, you are not adding length, even though the parameter is changing. So again, smooth is that the derivative is never the 0 vector. Nice. Let's do a recap of where we are. We know that we can describe a curve using a vector-valued function. We can put a restriction on the parameter t to have a beginning point of the curve and an ending point of the curve. Taking a derivative of the position function is extremely straightforward. Differentiate the component functions. You result in a vector, and we know how to take the magnitude of a vector. You sum the square of the components, and then take the radical of that sum. And we recall from all the way back in 1.2 a formula for arc length, where we have here updated the presentation of the integrand with this norm notation. Beautiful. Well, we can actually do something new. It's not all review. We can change the arc length formula to a function where this arc length function is measuring out a portion of the curve C, starting at the point A and then going to some arbitrary finishing point T, taking anywhere between A and B. And then that results in measuring length as a function of t, i.e. an arc length function, S of t. Excellent. Before we get into our next idea, let's go back and review again that in the video for 3.1 vector-valued functions, we looked at an ellipse. We parameterized the ellipse in 2 different ways, one resulting in the blue dot, one resulting in the black dot. The black dot corresponds with the parameterization, where the parameter is cubed, and the blue dot corresponds where the parameter t is taken linearly. In the video that we just watched, both the blue dot and the black dot correspond with the parameter t taken from a equals 0 up to b equaling 2 pi. The blue dot over that interval for t would trace the ellipse once, whereas the black dot would trace the ellipse multiple times. This is highlighting the notion that the arc length function S of t depends very much on the parameterization. So, what is the good parameterization? Well, instead of good parameterization, the term is arc length parameterization. And what we desire is for a unit change in the parameter t, we would like to observe a unit length change in the curve. All right, so let's do some examples. Here is an example from the book. We have the vector-valued function rvec of t given by component functions in the x slot for cosine t, in the y slot for sine of t. You should recognize that this is merely a circle of radius 4. Let's artificially place in a restriction on the parameter t, 0 to 2 pi, so that we trace the curve just once. We can recall from elementary geometry that the circumference is 2 pi times 4, or 8 pi. And then you see that as t varies over an interval of measuring 2 pi, the actual arc length is much greater, 8 pi. we desire a parameterization of the circle such that the parameter varying 2 pi will yield in 2 pi arc length of the curve, 1 to 1. Okay. So let's go ahead and take a look at how we do that. And we're going to actually derive this other elementary formula that arc length is simply S equals R theta. R, in this case, is 4, and we'll see that theta is going to be just t, the angle. Good. All right, so how do we do this? Well, we go and compute the arc length function, S of t. That's lower bound a, upper bound t, the variable on the left-hand side. For the integrand, we use the norm of a derivative on position. We look at what the position function is. It's made up of 4 cosine t and 4 sine t. Differentiating those, we get familiar derivatives. We're supposed to take the norm of this vector. We do so. In doing so, we notice that there are a pair of 16s that can be factored off, yielding a Pythagorean identity, so that the integrand is nice radical 16, or 4. This is a constant integrated from 0 to t, and thus we result in the integral evaluating to 4t. Noting that this is then the arc length function, we can write down S is 4 times t. Thus, we can solve for t as S over 4, and that's going to yield the arc length parameterization. That we take the t given and we swap it out for this expression, S of 4. Go ahead and do so. And here is the parameterization that we come up with. When we arrive at the arc length parameterization, we indicate that we have the good parameterization by indicating the parameter t as S. All right, let's try to drive home that point that we get a 1-to-1 correspondence in the parameter changing and length of the curve. Go ahead and take a derivative of this parameterization. Note that the chain rule computation is going to yield a multiplicative 1/4, which will cancel out the coefficient of 4 that exists. Take the norm of this derivative on position. Taking advantage of, again, the Pythagorean identity, we find that our prime vec is of constant magnitude, unit 1. That's where the bell goes off, unit 1. So that when you set up the arc length function, the integrand is going to be constant 1. And then evaluating with constant 1 integrand, the integral becomes simply the length of the domain of integration. So if you are varying t from a to some stopping point, that's a length of t, t minus a, and that will exactly correspond with the amount of arc length traced out on the curve. I.e., this is the characteristic of arc length parameterization. Nice. Here's an assignment. You want to repeat the example that we just did, but for this vector valued function, which gives a space curve called a helix. First, find the arc length function. Having found the arc length function, solve for t, and then plug back into the vector valued function. Beautiful. That was a clean glean of arc length.